So I'm going to talk about a project which is about how you can watch movies from a Netflix-like service without anyone, not even Netflix, knowing which movie you watched. The reason we want such a privacy-preserving service is multifold. So first, the use of on-demand Netflix-like services has increased drastically over the last 2 decades or so. For example, today, a Netflix user spends an average 90 minutes on Netflix daily. And in the process, generates a lot of data. For example, request trace containing the knowledge of which movies he or she watched, movie ratings, and so on. And this data, as we know, is usually stored in a centralized manner, where it is subject to high risks, such as hacks and accidental disclosures. Indeed, there have been real-world incidents. For example, we know that in 2006, Netflix released what it thought was an anonymized data set of movie ratings, but then researchers managed to de-anonymize ratings of several users. And all this is problematic because the knowledge of a person's media diet can reveal a lot of sensitive information. For example, political leanings, cultural affiliations, and sexual orientation. So the question we are investigating is, how can we build a Netflix-like media delivery system that meets these 3 requirements? So first, that provably hides the content of client's request, meaning that no one but the client knows which movie it is watching. Second, has a low dollar cost. So if the resource consumption of this system, for example, CPU, disk I/O, network, were to be translated into a dollar figure, then this cost should be a small multiple of the cost of a non-private system. And third, compatibility with commercial streaming. So the system must reuse and build upon existing content delivery infrastructure as much as possible. It must respect copyrights and other controls on content dissemination. Now, in building a system that meets these 3 requirements, our first step is to turn to private information retrieval, or PIR, cryptographic protocols. These protocols, as we know, allow a client to retrieve an object from a library of objects kept at one or more servers without leaking any information on which object is retrieved. They are promising because they meet our first requirement of hiding client requests, but they have several issues. The biggest issue is that of linear server-side overhead of PIR protocols. So for each client request, the server has to read from disk and process the entire video library. Second, there is a tension between overhead, server-side overhead, and compatibility. Specifically, there are 2 types of PIR protocols. One of them has lower server-side overhead, but requires multiple non-colluding servers in different domains, each having a copy of the library, which means that media content has to disseminate in a way that is inconsistent with how media disseminates today. The second type of PIR protocols do not have this content dissemination issue, but their server-side overhead is much vast. And third, there is an applicability issue, which is that PIR assumes that all the objects in the library are of the same size, but that differs from reality where media objects have different sizes. But we have built a system called Popcorn that meets our requirements by tailoring these PIR protocols to the media setting, by leveraging properties such as media streaming, media compression, long length of media objects. In particular, the per request cost of serving an object in Popcorn in terms of dollars is 3.87 times that of a non-private system, down from 265 times if you had applied PIR protocols as they are described in the literature. In the rest of this talk, I'm going to go into the background of PIR protocols, describe the challenges of applying them to a Netflix-like setting in more detail, and then talk about the design of Popcorn and the tailoring aspect. Okay, onto the background. So there are 2 types of PIR protocols. I'm going to describe one of them in detail and give only high-level properties of the other. So the first type of PIR protocols are called information-theoretic PIR, or ITPIR in short. They assume that there is more than one server, each having a copy of the library. They work as follows. So let's say that there are 2 servers, Server 1 and Server 2, each having a copy of a library with 5 movies, M1 to M5. And let's say that a client wants to privately retrieve the movie M1. Then the client does the following. So it takes this set of movie identifiers, call them 1 to 5, and then picks a subset uniformly at random. So this subset could be anything. So for example, it could be 3, 4, it could be 1, 2, 4, 5, or something else. And on average, this subset contains half of the total number of identifiers in the original set. Let's say for concreteness that the client picked the set 2, 4. It gives this set to server 1 and asks the server to XOR the movies identified by this set. Server 1 gives the reply back to the client. Now to the second server, the client gives the same request, except with one difference, corresponding to the movie that it wants to watch. So if the identifier for that movie is in the set given to server 1, it is excluded from the set given to server 2, and vice versa. So in this case, since 1 was not in the set given to server 1, it is put in the set given to server 2. Server 2 computes the reply, gives it back to the client. The client XORs the 2 replies to get back M1. Why? Because observe that M1 was input into this mix of XORs only once, while the other movies were either not input or input twice, which cancels them out. Now, ITPIR protocols are secure under the assumption that the 2 servers do not collude. If the 2 servers collude, then they will be able to figure out which movie user is watching by taking the difference of their sets. But otherwise, each server independently sees a random set of movie identifiers. And to prevent these 2 servers from colluding, they are usually put in a different administrative domain. So for example, server 1 could be Netflix and server 2 could be Akamai. Okay, so the second type of PIR protocols are called computational PIR. I'm only going to give very high-level properties of this type of PIR protocols. So instead of 2 servers, there is only 1 server. But this server, instead of doing cheap operations such as XORs, has to do much more expensive cryptographic operations. In practice, the state-of-the-art CPIR protocols are 7 times more expensive than state-of-the-art ITPIR protocols in terms of CPU consumption. Okay, so what are the challenges of applying these 2 types of PIR protocols to a Netflix-like media delivery setting? Well, the first issue with ITPIR protocols is that it disseminates media content in a way that is inconsistent with how media disseminates today. And this is because in order to prevent the 2 servers from colluding, they are put in separate administrative domains, like I had done with Netflix and Akamai, which means that one of the servers who's the owner of the library, Netflix, would have had to given a copy of its video library in plain text to a server that is in a different domain that it does not trust. Second, ITPIR protocols have cheap operations, server-side operations, XORs, which is good, but then each server on average has to read from disk and process half of the movies in the library. And this is because the randomly picked set of identifiers that a client gives to a server contains on average half of the total number of identifiers. And third, ITPIR protocols assume that all the objects in the library are of the same size, and this is because the XOR operation assumes that its operands are of the same size, and this is problematic, as I mentioned earlier. Okay, the CPIR protocols, the second type, do not have the content dissemination issue because there is only 1 server, but as I mentioned, this server is much more expensive, and CPIR protocols also assume that all the objects in the library are of the same size. Okay, so now given these 2 types of PIR protocols as a starting point, how can we build a system that meets our 3 requirements? That respects, more concretely, that respects controls on content dissemination and has low cost. Well, Popcorn's first design step is to somehow enable the use of ITPIR protocols because they have cheap server-side operations, but while respecting controls on content dissemination. And to do that, it composes CPIR and ITPIR as follows. So the owner of the library, server 1, creates an encrypted version of the library where it encrypts each object separately. So here, keys K1 to K5 correspond to the 5 objects, M1 to M5. And the encryption function could be any fast symmetric encryption, for example, AES. Now, server 1 gives a copy of this encrypted library to the server that is in a different domain. These 2 servers use ITPIR to serve encrypted objects to the client. Meanwhile, server 1 retains the keys that it used for encryption and puts them in a key library, and then serves these keys privately using the single server PIR scheme CPIR. Now, this composition between CPIR and ITPIR ensures that Popcorn respects controls on content dissemination. And this is because server 1, the owner of the library, gives a copy of only the encrypted library to the server that is in an untrusted domain. It also ensures that Popcorn has predominantly cheap server-side operations, and this is because it uses the lighter weight PIR, ITPIR, to serve large movies. So large movies go through the cheap XOR operation. And it uses the heavier weight PIR, which is CPIR, to serve only the much smaller encryption keys. So only small encryption keys have to go through the expensive cryptographic operations. Okay, so this composition addresses our first challenge and partly addresses the second issue. But it does not address the issue that the two ITPIR servers combined on average have to process the entire video library. To address this second issue, Popcorn's second design step is to batch requests. But how does batching help? Well, recall that in ITPIR, the client takes this set of movie identifiers and then picks a subset uniformly at randomly. And this subset, on average, contains half of the total number of identifiers, which means that when a client request comes into the server to generate the reply, it has to read through a major fraction of its library. Now, if a second client request comes into the server, then again the server has to read through a major fraction of its library. And again for a third request. So observe that the server is doing very similar I/O work, disk I/O work for each request. So instead of processing these requests separately, why don't we group them, process them in a batch while reading the library just once? This batching will not only amortize the I/O overhead, but it also significantly saves CPU cycles because the server's computation is now isomorphic to doing matrix-matrix multiplication, and matrix-matrix multiplication has much better cache locality than doing vector matrix multiplication. Okay, so Popcorn has an interest in batching client requests and forming large batches. And that raises a natural question: how should client requests be batched? After all, different clients watch movies at different times. Well, one strawman design is to group all requests that arrive at the server during a fixed time interval called an epoch. So let's say that the horizontal bar here represents time, and the vertical arrows represent requests coming into the server. Then divide time into epochs, group all requests that arrive during an epoch, and handle them in a batch during the subsequent epochs. Now, from the client's perspective, this arrangement looks like the following. So initially, there is a delay during which it waits for the server to form a batch. And in the worst case, this delay equals the size of the epoch. Then there is an additional delay during which it waits to download the first playable piece of the movie. So in the worst case, the client perceived delay equals the size of the epoch plus some upsilon time. Now, coming back to the server, there is a choice on the size of the epoch. So on the one hand, it can choose a small epoch, which means that the client perceived delay will be small, which is good, but then the batch sizes will also be small. On the other hand, it can choose a large epoch, which means that the batch sizes will be large, which is desirable, but then the client perceived delay will also be large. And that is problematic because we know that modern media delivery systems like Netflix can start playback within a few seconds. The fact is that there is no good value for the epoch size, one that gives both a small delay and a large batch size. So to address this classic systems tension between wanting large batches and a small delay, Popcorn leverages this property of media, streaming. So to give an intuition, let's revisit how a client actually streams a movie in today's world. So if a client clicks on the play button at time t equal to 0, it needs the first piece of the movie immediately at time t equal to 0. If tau is the time it takes to consume a piece, a chunk, it needs the second piece of the movie at time t equal to tau, third at time t equal to 2 tau, fourth at time t equal to 3 tau, and so on. So observe that the client needs only the first piece, the first chunk immediately, and that dictates its perceived delay. It does not need the latter chunks immediately. In fact, the times at which it needs those chunks increases with the chunk number. Now, an ITPIR server can exploit this fact to form large batches while keeping a small delay, as follows. So instead of treating each movie as one long piece, it splits it up into increasingly sized pieces. So for example, the first piece might contain data for first few seconds of the movie. A latter piece might contain data for tens of minutes of the movie. It splits up all the movies similarly. and groups them into columns, where there is a separate ITPIR instance for each column. Now, the important point is this. So the first column is kept narrow, which means that when a client request comes in for XOR of some of these movies, the first piece of the reply can be generated quickly, so the client sees a small delay. Latter columns are wider, which means that to generate that part of the reply, the server is going to take longer. But that's okay, because there was more time budget in the first place. The client did not need those pieces immediately because of the streaming pattern. But the good news is that while the server is going through its column to process the client's request, more requests from different clients are arriving in the background. And the next time the server takes a trip, it can process all of them in a batch. And these batch sizes are big because we took a long time to go through that wide column. Essentially, batch sizes grow as we progress through the library. Okay, so Popcorn batches client requests to amortize the overheads of ITPIR. And it forms large batches while keeping a small delay by leveraging streaming. But there is one more challenge that we must address, namely that PIR assumes that all the objects in the library are of the same size. So to address this challenge, one straightforward solution would be to pad all objects to be of the size of the longest. But the solution has really high network costs. So for example, in Netflix, the average movie length is 90 minutes, whereas the longest movie is 6 hours, which means that the average size of the padding that would have to be downloaded over the network is 3 times the average size of the movie. So instead, in Popcorn, we use another property of media, compression, or the ability to change video bitrate, as follows. So let's say that the horizontal bars here represent length of the media objects. Then choose a representative object, O average, whose length is closest to the average size object. Pad objects that are smaller to O average's size. Compress objects that are longer up to a cutoff by reducing their bitrate down to O average's size. And then split up the longest objects into multiple ones. Now, the solution works for 2 reasons. So first, research shows that small variations in video bitrate have a limited impact on user satisfaction. Instead, factors such as playback interruptions and buffering events affect user satisfaction negatively. And second, our analysis of Netflix's catalog shows that most of the objects are close to the average size object, which means the amount of padding or the compression that they require will be small. Okay, so now that I've talked about the challenges of applying PIR protocols to a Netflix-like media delivery setting and how we overcome these challenges in Popcorn, I want to talk about the quantitative benefits of Popcorn's techniques. And to do that, I'm going to compare Popcorn to the following 4 baseline systems. So a non-private system that simply serves chunks of the movie using an Apache web server. This models the status quo. Then XPIR, which is the state-of-the-art CPIR implementation. I'm simply going to refer to this system as CPIR. Then Percy++, which is the state-of-the-art ITPIR implementation. I'm going to simply refer to this as ITPIR. And then ITPIR++, which is ITPIR extended with the epoch-based strawman batching scheme that I had described. I'm going to compare these systems for a Netflix-like library that has 8,000 movies. Average movie length is 90 minutes. And average movie playback rate is 4 megabits per second. The workload is 10,000 clients arriving within 90 minutes, according to a Poisson arrival process. And for each of these systems, I'm going to report a per request dollar cost. And to estimate the dollar cost, I'm going to measure the resource consumption, like CPU, network, I/O, and then convert it into a dollar figure using a pricing model derived from Amazon EC2's pricing model. So if we use CPIR, the heavier weight PIR directly, then the dollar cost is really high. It is 265 times that of a non-private system. And the reason is that the CPU and I/O overheads are just ridiculous. For example, for each concurrent request, the server needs 12 CPUs and 64 gigabits per second of I/O bandwidth. Now compare this to the I/O bandwidth of modern hard disks, which is roughly 1 to 3 gigabits per second. Instead of using CPIR, if you use the lighter weight PIR, ITPIR, then the CPU overhead comes down somewhat because of the cheaper server-side operations, and so does the dollar cost. But still, the dollar cost is way too high. Batching can help us amortize some of these overheads. So if we extend ITPIR with the strawman epoch-based batching scheme that I described, then the CPU and I overheads come down drastically, and the dollar cost as well. But still, the dollar cost is not at a point where it is a small multiple of the cost of a non-private system, which is what our initial goal was. And the reason is that with an epoch size of 15 seconds, the batch sizes are just not big enough for effective amortization. Now, Popcorn's batching scheme allows us to form large batches while keeping a small delay. And it gets the CPU and I overheads down to a point where the dollar cost is a small multiple of the cost of a non-private system. And I want to quickly remark that 3.87 is a pessimistic number for Popcorn. A more optimistic number using some recent techniques is 1.5x. Okay, so Popcorn provides strong privacy properties. It hides the content of client's request at affordable costs, but like any system, it has some limitations. So one issue is that it assumes that the ITPIR servers do not collude. So if they collude, then they will be able to figure out which movie a user is watching. Second, Popcorn's costs, although amortized, are still linear in the number of movies in the library, which means that although it can scale to Netflix's library, it won't be able to scale to YouTube's, which has hundreds of millions of movies or videos. And third, Popcorn's current prototype does not support things like movie recommendations and aggregate view statistics, but this is not a fundamental limitation. There is prior work that can do recommendations in a privacy-preserving manner, and this can possibly be incorporated into Popcorn. I want to quickly go over some related work before concluding. So there is a lot of work that tries to improve the performance of PIR protocols that addresses the content dissemination issue and handling variable-sized objects. And there are numerous PIR implementations. We borrow both code and techniques from these works, but none of these works address the resource overhead, server-side resource overhead issue of PIR protocols at the scale that we target in Popcorn. Okay, so to conclude, we asked the question whether it is possible to build a Netflix-like media delivery system that hides the content of client's request, that has some basic functionality of serving movies, obviously, and that has affordable costs. It seems that the answer is a cautiously encouraging yes. We can get there by tailoring PIR crypto protocols to the media setting by using things like media streaming, media compression, and long length of media objects. And the per request cost in terms of dollars of serving an object in Popcorn is 3.87 times that of a non-private system. Okay, thank you. Questions?
Yes. Very interesting work. I see you optimize a bunch of efficiency metrics for the PIR scheme in some sense. One metric seems missing here is the communication. Especially for your basic scheme, at least you need, say, for the private scheme, you need at least 2 times communication of non-private scheme. This is a particular problem in the movie downloading case. Say I watch a high resolution movie, 10 gigabytes, even more than that. So what's your take on this?
Right, so that's a concern that's accounted for in 3.87x because 2x comes from the network. But I will add that there is a recent technique which allows us to get this down to even 1x. So the two servers among themselves can communicate without breaking privacy by using pseudorandom generator. There's a technique, there's a paper Riffle recently, and so if we accommodate that technique, the network overhead is going to come down from the server to the client to 1x. That's it, like just the cost of transferring the bits of the movie, that's it.
Elena, or Shai, whichever.
I have a couple of questions. I'm curious what happens when M1 turns into a request like, I want to see more movies like M1, right? Or the recommender system. Is it as simple as the system you'll still do this like M1 and M3, let's say request one and M3 the other, and then the system will give you the similar ones back? Is it as simple as that?
So
or is there
I'm not sure if I fully internalized your question, but
So in this case, you're not trying to hide. You have seen M1 already, and you want to see more movies like M1, and you don't want the system to know that.
Right.
And so, is it as simple as like I still put exactly the same request in, except that I ask for movies like this?
so you'll not put the same request in. You'll put a similar in the sense that it will again be randomly generated. So if let's say if you were to watch M1 twice, right, one after the other.
No, I'm asking the system to recommend me movies in this.
Oh, so recommendation. So what I talked about was not doing recommendations, right? It was just like retrieving the bits of the movie.
I understand that. I'm just trying to see if we can extend this further and think about how this would work in a recommendation case.
Right.
Where I'm now asking for recommendations for movies like M1.
Right. And so I don't think we can use PIR protocols there for recommendation. We'll have to use some other technique.
Why not?
Because I think PIR is about retrieving. Actually, we might be able to use PIR protocols. Let's say if there were a database, we won't be able to do. We might not be able to do collaborative filtering in some ways, but if there were to be a database at the server which said M1 and related movies, right? So then you could possibly use PIR to get those related movies, the list of related movies, right? But that's based on content-based recommendations, just plain content.
The service would still be on the server side, it would not be on the client side. But thinking about that also, right now if we let's say return the 3 most similar movies to M1, and 3 most to M2, and 3 most to M3, because I requested those 3. Thinking about it that way made me think of something else. So usually you don't want something to be known because it's potentially sensitive in some way.
Sure.
So it may be like different, these 3 movies that were just got recommended back may be very similar and different from the other movies, and put that.
But the server won't know, right? The server won't have any idea what was retrieved. Even the recommendations, what was retrieved, or the movie that was downloaded. Because of the properties of PIR protocols, right?
Because it's encrypted?
Yeah, I mean, the request is either encrypted or it's like indistinguishable from random, right? Right. So in the ITPIR scheme, for example, the client is sending like a random list of movie identifiers to one server, like generated completely randomly, independent of which movie is being watched, right? And to the second server, it's sending that plus minus the movie that it wants. So you can think of first server as like a one-time pad.
Right, but what I'm saying is that extra movie you're adding is no longer a random movie because it's sensitive in nature, right? So potentially the server now can say, oh, that movie is not seem like a randomly picked movie, or it's different because it's sensitive in some way. So that would be my guess that it's a sensitive movie.
So I'm going to suggest that we
I guess
just the move the discussion of the fine points to later.
I'll ping you. Like
I think it'll take a while to converge to this particular. Shai.
If you look at other applications, the typical thing that people put in their introduction is pattern database or things where you need to, you don't retrieve by index, by name, but rather you retrieve by search or things like that.
So we did not. So when I started, I was like, okay, I'm going to try to build this thing just for Netflix, so tailor it quite a bit. So I did not look at PIR, applying PIR to like patent databases or anything, or PIR with keywords for search purposes. I haven't looked at yet. But in future, I might want to look at private web search in some ways. So going into PIR with keywords kind of a thing. Not SSE stuff because the client can encrypt the database, but like there's a public database, but you want to retrieve based on keywords efficiently.
Question. I have a question. So I guess I had 2 questions. So one, and I have a feeling I've asked Mike this question, I don't remember the answer.
Okay.
Doesn't the length of the movie, even approximately, like say if the length of the movie leaks information.
Mm-hmm. So
right?
Sure, length of the movie without doing anything will leak information.
Right.
So what we do is make all of them the same size, right?
Okay.
So you do some pad
Is
some.
that accounted for in your cost?
Yes. So we assume that. So in this resource cost metric, yes, but there is a different cost that one has to pay, which is like if we compress some of the movies, right, a little bit. So there will be cost in terms of quality, little bit, right? In terms of viewing experience. So that is not accounted for in the 3.8.
But also, like the fact that I'll leak a bit of information. I have children who use Netflix, and they watch short things generally.
Right.
Or they watch a mix of very short things and very long things.
Yeah.
Right. So if you make everything the same length, doesn't that mean that those short things become those 5-10 minute videos suddenly they're 2 hours long?
Yeah. Yeah. So 90 minutes. So yes, that is included here. Yes.
Okay.
So yeah.
And my other question is, Netflix is not just like one server.
Sure. It's a CDN. Yes.
Yeah. Right. So to what extent is ITPIR compatible with the way that people engineer CDNs now?
So I think it's compatible. So even the request workload that we chose was based on what it is, right? So what would happen is there would be like a CDN network, right, with multiple servers. Each of them, I'm assuming, will have an entire copy of the video library.
No, but is that the way CDNs are actually engineered?
Netflix is yes. Today now, yes. So Netflix has something called Open Connect. They recently have deployed their own big boxes with like stacks of hard disks, and then that has the entire library. So, but in order to deploy it's compatible theoretically, yes. But in order to deploy this, we'll have to move more CPUs into that box as well, right? Because we're increasing the servers.
No, but I guess I did not think that Netflix had like many full copies. I assumed each server had like a subset of the.
No. So the recent.
For load balancing purposes, but you're saying that's not the way it works.
No, the way it works is with the Open Connect CDN, they have their full boxes. Yeah.
Other questions? Okay.
Okay. Thank you.